Okay, so I'd like to first thank the organizers of the entire program, as well as this 2-week theme. Okay, so it's a great pleasure. I mean, I've never been to Paris before. I mean, other than just connecting flights and so on. So I mean, it's really wonderful, and the program really, I mean, seems that it let us talk to each other. Okay, I mean, using different languages and so on. So I like that a lot. Okay. So I mean, in case you raise kids in US, then you'll probably recognize this. Okay, it's Madeline. So yeah, Paris is home not only to Curie and Poincaré, but also to Madeline. Okay, so I pick it up. So today I'm going to talk about, fundamental inequalities and upper bounds. Okay, I mean, it was a joke, of myself because lower bounds for some people can be upper bounds for other people. Okay, so here is what network information theorists typically care about. So we model the network with n nodes by some conditional probability distribution. Okay, so there are n nodes with input, say, xj and output yj, and the input-output relationship is completely specified with this. So you can capture, say, noise in the channel, interference, broadcast, multiple access. In general, you can capture the entire topology of the network, right? And what we really care about, there can be more ambitious goals, but at the minimum, what you want to learn in the end is, say, what is the capacity? What is the maximum data rate we can communicate over this network, again, specified by this, reliably? Okay, so that is a network capacity question. And another question is, related, but not exactly the same. What kind of coding scheme that achieves this network capacity, the fundamental limit? Okay, and I say it is the ultimate goal, but you can ask further questions. What can really happen if you have a finite block length, or how do you reduce the delay and so on? But I think this is a first-order question that is important to many people. And the bound that controls the capacity problem is open, and I'm pretty sure it will remain open for centuries, okay, if people care about them in centuries. But there are still some useful bounds. Okay, so here is one bound. So we first decompose the network into two parts, say S and S complement, right? So do it arbitrary way, and then we look at the mutual information between the inputs on S side and the output on the other side, conditioned on the input on the other side, right? And we minimize this mutual information, the conditional mutual information, if you will, okay? And we make this cut so that this S and S complement each contain the source and destination. And then we maximize over all possible input distributions that can be induced on the n inputs of the channel, and then that is the upper bound on the capacity. And this is the famous Cossette bound by Abbas El-Gamal. We can interpret this, and again, these are nice mnemonics, but they don't necessarily really mean mathematical truths, but the interpretation is the following. This is the amount of information the nodes in S can transmit to nodes in S complement, obviously. Or you can actually think of it as the amount of information nodes in S complement can receive from nodes in S, right? And again, these are mnemonics. Mutual information is just mathematical quantity. It doesn't really mean anything. It doesn't really mean it is an information about something. That is a second thought. That is because Shannon and other people proved some mathematical theorem, then we can attach that kind of interpretation. But these are two mnemonics, which at this point seems to be compatible with each other. So what happens if there are multiple flows, right? So we can think about many flows. Here we have some message M1K. Actually, I'm told to use this mouse. So where is my mouse? Say, there is a message that is going from node 1 to node N. There is another message, going from node 1 to, say, node K. And there is another message going from node 2 to node J, and so on. So there can be multiple information flows, right? And now when you have a background channel, what I'm going to do is I'm going to put the channel into the background, and I'm just going to look at the flows using this graph. So there are, say, n nodes, right? And there are edges which represent the flows. right? And I mean here, I'm making every flow into a unicast, which means that it's going from one source. So the message is available at one sender, and it is required at another single node. Okay. In general, you can always think about subset to subset communication. So in general, roughly there are 3 to the n. So for n node network, there are roughly 3 to the n different messages, flows you can think about. But here we are limiting ourselves to unicast flows, right? So this is the flow diagram of the network. And then the cassette bound by Elgamal extends in the following way. So again, we decompose the network into S and S complement, right? Then the sum of the flow rates that is cut by SS complement. So again, this is the, sum of all flow rates, okay, that is cut by SS complement is again upper bounded by mutual information between X on S and Y on S complement, right? And we do it for, so for every S, this inequality is satisfied, and then we have to take the union over all possible joint distributions. So that is a cassette bound on the rates. So there can be rate tuple. So now it's a high-dimensional trade-off between different flow rates. Then this trade-off can be captured by, for fixed joint distribution, we have set of linear inequalities, right, which is in fact a nice polyhedral shape. And then we take the union over all possible joint distributions. So that is a cassette bound, right? And the complete proof can be found in Cover and Thomas. So this is very nice result. I mean, very, very simple. And again, we can attach the meaning to it. I mean, it's very intuitive and also very general because we didn't assume anything whatsoever about the underlying network. So in some sense, this is one of the fundamental inequalities in network information theory. When we limit our attention to very simple networks, such as Gaussian networks, so here every y can be represented as some linear combination of x's plus some additive Gaussian noise, right? And then we call that as Gaussian network or Gaussian relay network, right? And multiple access means that there are many sources communicating to a single destination. So in that case, we can actually show that this cassette bound is uniformly meaning that for any Gaussian parameters you give me, the noise powers or channel gains, uniformly we can actually attain the cassette bound within 0.63 n, where n is the number of nodes again. And this is the best known bound, the general bound. Okay, so that is possible. So cassette bound is not too bad, right? Even though we don't know how to characterize the capacity exactly, but at least approximately we are fine. Okay. More recently, we also found a dual result, which shows that the broadcast case, so here now we have a single source which has all the messages, and each of the messages are required by different receivers. And in that case, we can actually have a slightly better gap, so we can get half n as a uniform bound on the capacity. And again, so that is a gap between what we can do and the cassette bound. The truth may lie in between. So for these simple cases, either single source or single destination, the cassette bound is reasonably good. So what remains is how to solve multiple unicast. And for that case, actually, we don't know. The cassette bound seems to be abysmal. And what we can achieve, I mean, we don't know how to actually do anything here. Okay. And here is one attempt to tighten the cassette bound, which we call directed cassette bound. So again, we go back to the network diagram. There is an underlying channel or network given by conditional probability, and this graph denotes the set of flows. Instead of decomposing the network into two, now we are going to partition the network into multiple groups, multiple subset of nodes, right? And then we look at all the flows that is going from top to bottom. Okay, say here there is one flow that is going from second floor to first floor. And since this is Paris, this is ground floor is 0th. not in US system. Okay, so here there is a second to first, first to ground, okay, and then second to ground. So these are flows that are cut by this partition, right? So we look at all the flow rates.
You mean the direction of the flow is arbitrary? What is going this is a top flow?
So you can induce arbitrary partition. Okay, so any partition. So you have a graph, okay, then you put the nodes in any floor, and then look at all the flows that is going from top to bottom. Okay.
But you can reverse it. You can reverse it.
Yeah. I mean, if you move these nodes, for example, 3 is here, 4 is here, then you are cutting another flow. Okay. So any flow that is going from the higher floor.
Is it okay.
This is a flow diagram. The physical network can be anything. Okay. Right? So I'm just drawing the graph that represents the flow, and I partition the nodes in a way that they are partitioned into different floors, with some direction, say top to bottom, and then I look at all the flows that is going from top to bottom.
I see.
Okay?
So
right?
So you ignore the light blue ones, the 2 arrows?
Yeah. So there is a flow here, but I mean this one is not really cut by it because it's going in the wrong direction. Okay? And here it's in the same floor, so I don't count. So I look at all the flows that is going from higher floor to lower floor, and then what we can show is.
So you can do this independently of the edges.
What do you mean by edges? The underlying graph.
Yes.
Yeah, underlying graph hasn't been here yet. So this is a purely flow diagram. Yeah, right. Yeah. So this is a logical thing, and now let's bring in the physical layer to the picture. This one actually can be upper bounded by some object. Many of you haven't seen yet, and this is so-called directed information. Okay, so directed information is a generalization of information when there is some causality between the symbols. Okay, but here there is nothing temporal. Here I'm inducing causality, or say spatial causal relationship from the nodes by just looking at writing this as output in this flow, output in this flow, and output in this flow. Okay, so. Yes.
Why from Y to X instead of from X to Y?
Oh, here.
Yeah.
So now I'm going to give you the interpretation of this. Okay. So when you think about mutual information between X and Y, as we argued before, it can be interpreted as either what X can transmit to Y or what Y can receive from X. Okay. So that is, again, common mnemonic. As I told you, it is just a myth. Okay. Right? Some authors even wrongly argue that is interpretation or that is how you prove coding theorem, but that is all wrong. Okay, coding theorem is there just because we proved it. But here, one interpretation we can give to this from other work on directed information is actually this is the amount of information Y can infer from X in a causal manner. Okay, so there is a Gambling interpretation of all this directed information and so on. Okay. So this is what we call directed concept bound, okay? And this is not the main point I'm gonna try to, bring in this talk. So I'm just gonna give you this notion, and if you are interested, you can actually read some of the references.
What sum rate are you talking about?
Again, sum rate is the flows that is cut under this diagram. So this rate, and this rate, right? And if you reshuffle them in different, okay. Buildings. So if you put them in different buildings, then different flows will be cut. Then there will be corresponding directed information, and again, that is a bound. So that is a directed concept bound, right? And the previous concept bound, the undirected concept bound, is a special case when there are only 2 floors, S on top and S complement on the bottom. Okay, so again, I claim that this is a simple intuitive and general result because it works for any network whatsoever, right? And my hope is some computer scientists find this result interesting and try to use them in their field, okay? Because things like this happen a lot actually. Even some of the circuit complexity results actually use the Coset argument, and this is a generalization of it, right? And when there is a single source or single destination, it's actually exactly the same as Coset. Yes, question?
The Coset argument is used in circuit complexity, but do you see information theory version being used in one of the papers? Are you claiming that?
Yes, Actually, there is even, some people actually looked at the area required or connection requirement for decoders, for example, and there people had to use cassette. Yeah. So there is a paper by Green, El Gamal, and other people. Okay. I mean it's a long time ago. I think it is probably early 90s and so on. Yeah. And recently there is actually more result coming from who's the guy at Carnegie Mellon?
Pulkit Grover.
Yeah, Pulkit Grover has been using some of these arguments as well. Yes.
So this is not a single letter problem.
No, it's a single letter.
It is single letter?
Yeah, everything is single letter. Okay, so there is nothing temporal. Okay, it's spatially causal. Yes, yeah. Right. So I mean, some of you actually know directed information in the context of feedback communication and so on. And there it is a multi-letter. You have to take the limit and so on. There is nothing. Here it is just simply we are looking at these variables some direction. Yeah, there is some direction. Okay, that's all there is. Yes.
Can you written by this x mu naught is singled out condition? Why do you do condition on x of mu naught?
Oh, okay. So this is what is here. So whatever if you go back to the original concept bound, we again have this condition. So this can be interpreted as everything decoders on this side already know. So it can actually use it. I mean, you can call it a success cancellation decoding, if you will, but it's the information that is already there. Okay. So we can incorporate that information. And again, these are all interpretations, nice mnemonics. In the proof, it actually follows naturally. Okay, so, and for multiple unicast, actually, this is the most interesting part. For multiple unicast, actually, this one strictly improves the concept bound, okay, in many ways. I mean, if you look at the highest signal-to-noise ratio, Gaussian networks, then it actually achieves the better degrees of freedom. When you talk about network scaling law, where you increase the number of nodes in the network and try to see how the capacity scales, then again, we have an example where we have way better, say, log n to n improvement in scaling law. Okay, so this is, in my opinion, one of the fundamental results in network information theory. Okay, so the question is, what is next? I mean, where can you go from here? And this question was raised by Gerhard Kramer when I explained this to him, and he is one of the network information theorists. So, I mean, can you actually have a general program to bound the network capacity? I mean upper bound. And this talk is actually an attempt to answer his question. And I'm actually going to go to something much, much simpler, which is called index coding. Okay? And if you haven't heard about index coding, I'm going to give you the self-contained description of the problem. Right? And this problem is very, very simple. I mean, I can explain it even to my daughter, I think. I mean, if she listens to. Okay? And then I'm going to talk about a few lower bounds. I mean, very simple lower bounds. Actually, the literature is very, very rich here, even though it is a simple problem. I'm going to pick out a few, which is sometimes used as, a metric, okay, or a benchmark to compare the upper bounds, and then I'm going to focus on the actual upper bounds, okay. And here actually things are far cleaner than the general noise network. So, is the outline of the talk clear? All right. So here is the index coding problem, okay, and the problem goes back. I mean, I've been tracking history of the problem. Raymond actually helped me recently. So it actually, the famous version came from computer science community, theoretical computer science. So Birk and Cole, looked at the broadcast problem, okay, satellite broadcast problem. So there are, say, 3 movies at the access point, or satellite, okay, and there are 3 receivers, each wanting one message, one movie each. So the top one would like to get blue movie, and this one would like to get the red movie, and this one would like to get the green movie. Okay, but because they already have some prior knowledge, so the top one has red already, and this one has green and blue, and this one has, say, blue already. Okay, and the question is, what is a fundamental limit on the number of transmissions? Obviously, if you use 3 transmissions, say 1 transmission per movie, so that is our unit. Okay? So if you can transmit 3 movie worth of data, then everybody is happy. The question is actually we can do better, and turns out we can do better. Here the best we can do is actually 2. So instead of 3, say we have 33% throughput reduction, okay? Data transmission rate reduction. How do we do it? through network coding, we already know how we do it. Here, if you look at this guy and this guy, their side information, what they need and what they have is complementary, right? So in that case, if you represent the data in any group here or finite field, okay, more specifically, then if we send the sum of the data, okay, then we can actually subtract off what he or she has to recover what they need, right? And X3, I mean, we just transmit as on its own. Okay, so this shows that we can do 2, and 2 is the best. We can represent this problem in one of the network coding problems. So here, these edges mean the connectivity. So we can say transmit 1 unit of information from, say, this node to this node and so on. Okay, and then here, there are 3 messages and 3 demands. And then these internal edges denote the side information pattern. Okay, so for example here, node 1 already has message 2, okay, and so on. And this middle link is actually the bottleneck link. So it has all the messages, and it would like to broadcast it. And this one really captures the encoding operation we are doing here. So here, this one requires to transmit 2 units of information to satisfy everybody. Or if you fix this edge as 1, then the rate we can communicate, the movie size should be half of the link capacity of the bottleneck link. So this is index coding problem. I'm going to define it more formally in the next slide. But if you look at this and just highlight on this connectivity pattern, because that really captures all about index coding, and there's no reason to separate this node and this edge. So if you just wrap them around, then you get a nice directed graph. So here, edge going out is, say, node 3 knows the message 1, and so on. Okay? So if you count all non-isomorphic directed graphs, okay, then that is exactly the number of index coding problems we can get out of m messages. And there is a more general version. Here we require each message has only 1 destination, but there is a more general problem definition. But we'll stick with this unicast definition, and then the number of problems grow super exponentially. So this is a very, very rich problem. And of course, we are interested in understanding these 2 questions, the fundamental limit, okay, and the coding scheme that achieves it. So formally, for n messages, so here's a notation, x1 up to xn, we are going to encode it into some bits. Okay, and each decoder has some side information, say A1, A2, which of course doesn't include what we have to get. Right? So we are going to parameterize the code by T and R. So T is the number of bits in your movie files. R is the number of bits we have to broadcast. Okay, and the decoding map is based on side information and what is broadcast, we want to recover our desired message. We look at this rate, R over T, the number of bits we have to transmit per movie bit, as broadcast rate. And I mean, it's a funny language, but historically, the optimal broadcast rate is called broadcast rate. And we call that as beta. So we want to look at all possible codes and want to minimize it. Sometimes we want to look at the reverse quantity. We want to actually maximize the amount of movie size given once you fix the code size. And that is called capacity or symmetry capacity. And this broadcast rate is the reciprocal to symmetry capacity. All right, so this problem actually is very, very rich, even though it sounds very simple. Okay, anybody can understand the problem. It actually has applications in satellite communication, which I mentioned. The Noga alone and others motivated the problem through multimedia distribution. Okay, and in physical layer wireless, it can be actually used to capture some of the interference management programs. And there is some applications in coded caching. When you are caching some data, it actually helps you to store some coded version instead of the vanilla version. There are many related problems. Okay, so the network coding problem, and as you argued, this is actually a special case of network coding. Okay, but Salim El-Ruyab in two references for linear coding and general coding, he could relate this problem into network coding. So to be precise, if you know the linear coding, so linear coding means that we assume all the message symbols are vectors or scalar or vector of finite finite field, and your coding operation is all linear in that field. Okay, so in that case, if you know the network coding capacity in general, then you can answer index coding capacity. And vice versa, actually. If you know all index coding linear capacity, then you can actually solve any network coding capacity. For nonlinear problem, the relationship is a little more subtle. Okay, so their codes can be related nicely, but their capacity cannot be related exactly, but at least we can use index coding capacity to upper bound network coding capacity. So this is, again, nice upper bound for index coding can be actually used for network coding. And this idea actually goes back to Henri. So he's here next week, I believe. Oh, he's here? Oh, okay. So then, yeah. Anyway, so he actually also observed the same thing, but in the context of a little bit different problem. But that can be all identified as index coding. Okay. And then there is a relationship to distributed storage. So when you are storing data, you want to take multiple copies, and we want to make sure that, say, for example, if 1 is broken, then we would like to recover it from 2. Here, when 2 is broken, then we want to recover it from 1 and 3, and so on. Okay, so when there is a local reconstruction requirement, this problem can be actually related to this problem in a very intimate manner. Okay, so solving this will solving index coding will solve this, and vice versa. There is a related puzzle, okay, or recreational mathematics problem by Henri. So it's a head guessing problem. So you have a bunch of players who have some local view of other players, and individually they have independently and randomly chosen head colors, and they want to guess their own head color. And the team wins if everybody is correct. And this problem is called guessing games on graph. And this one is, again, related to index coding and distributed storage. And finally, the Shannon asked the question of achieving zero error when we have some noisy channel. Okay? And if the channel is arbitrarily connected, then it is not so good. But if there is sparse connection between the input alphabets and output alphabets, then we have non-trivial capacity. So that is called zero error capacity. And Hamers had an earlier work that relate min rank with Shannon capacity as an upper bound. And the Shanmugam, Dimakis, Langberg, as well as our group, is investigating the other connections to this problem. So the problem, even though it is very, very simple, it is kind of the problem in network information theory. So let's look at the lower bounds. I mean, here is my way of looking at all possible coding schemes. Not all possible coding schemes, major coding schemes that was introduced in the literature. Okay. Roughly, there are algebraic techniques, okay, typically using some linear codes, right? And there are some graph theoretic numbers, okay, or quantities which can be associated with some coding scheme, and as well as there is a random coding scheme. And I'm going to focus on two coding schemes. One is fractional clique covering, and the other is composite coding. And again, I'm just going to convey basic ideas without getting into any details. Okay? So first, let's look at this graph. So 1 and 2 know each other, and 3 doesn't know anything. And now for this problem, what we can do is we can decompose the graph into two pieces, say 1, 2, and 3, and you notice that 1 and 2 form a clique, and 3 is clique on its own. And whenever you have a clique, since you know everybody else in your clique, that means that if you send the sum of all the data, then you can always recover what you need. Okay, so here per clique we send the sum, okay, and what we need to transmit, the broadcast rate we can achieve is actually the number of cliques that covers the entire graph. So in general, we can minimize the number of cliques that cover the data, cover the graph, and that is what we can achieve. And this is called the clique covering rate or clique covering number. This can be characterized as an integer program. So look at all the cliques, right? And every node should be in at least one clique, right? And we want to minimize the number of clicks. We can relax it as a linear program. So instead of having a full membership, we can actually have a partial membership, but still we have the covering condition satisfied. Then what you get is fractional click covering number. And this is, again, a valid coding scheme. And the reason is we can do the time sharing between different coding schemes. So as long as your timeshare is actually covering all the movie file you have, then you have a complete transmission. Okay? And this is much better because we improve the rate, and this is easier to compute because it's a linear program. And this result is due to Blasiak, Lubetsky, and Kleinberg. So this is the basic coding scheme. And a lot of times, we actually use this as a benchmark. Here is another coding scheme due to my research group. Oh, by the way, co-author of this talk is actually my student Fatame. So she did most of the work here, and I'm just making it sound nice. Okay, so here we actually use the random coding idea, which goes back to the original paper by Alswede Chai, Lee, and Young. It's a network coding paper. And in some sense, random coding makes a lot of things easy, okay? Because pretty much everything is almost MDS. So here is how we do it. So there are n messages. Then we look at 2 to the n-1 subsets. And per subset, we actually think of them as separate encoders. And each encoder does a random hashing of its member messages. So for example, here, the last encoder has subset that includes every messages. So then we do the random hashing of that. Here, say there is an encoder S, then it does the random hashing of messages in that set, right, at a certain rate. And then in the next stage, we do another round of random hashing, okay? And we do control the hash rate so that everybody can actually recover its desired message. So if we do that, then the solution of this rate requirements can be actually found as a very simple linear program. Okay, and it has a nice polymetric structure, so the computation can be done, in a reasonable manner. If you think about it, the number of variables is actually exponential in n. So I wouldn't say it is very efficient, but at least we can write it out. And we can actually show that this one is optimal up to 5. So there are around 9,000 problems up to problem size 5. It is optimal in, say, symmetry capacity, but actually entire capacity region. But it's difficult to scale. And as expected, if you go a little larger, then we can find counterexamples.
You mean a difficult scale, meaning that scale the computation of the region?
Yes. So it's difficult to, this is more or less, numerical result, right? Computational result. So it's true, but when you are given arbitrary instance, it's hard to write, evaluate it and say how far it is from the optimal and so on. Okay, so analytically, it's not scalable. And also, if you increase n, then it is not optimal. Actually, we can find instances, I believe, going from 6, there should be some instance where actually this is suboptimal. Okay, so that is the lower bound side. Yes?
I'm not familiar with random coding. Can you explain a little bit more?
So random coding here is the following. Suppose that, say you pick one number, out of, 100, and I pick one number out of 100, okay? Right? Then what is the probability that we collide? That is 1 over 100, right? Okay. So that is a random coding, basically. But we haven't really specified how you do the mapping.
I don't understand. You said do a random hashing, but how do you decode? Because if it's random, how do you?
No. Actually, random coding. So if you are not used to information theory, you probably heard about random coding some point. Okay. So random coding is the following. So the probabilistic method. Okay. Actually, what Shannon did was Shannon discovered it himself. So he wanted to find the good code, right? But good code was extremely difficult to find. At least back then. So what he did was he randomly generated a code, and of course everybody knows the code book. So the proper language is random codebook generation. So they all generate codebook at random, okay, and look at the average ensemble performance. And if ensemble performance is good, then there must be at least one good code. So that is random coding. So here I'm doing the random hashing and look at the average probability better, just like we did analysis, right? Okay, and since that collision probability is sufficiently small, so that means that there should be one good code. And for this particular problem, there is a technique of going from positive small error probability to 0 error probability. So.
But actually building the encoders and decoders would be expensive because you're choosing random things, because your codes are random.
Yeah, but at this point we don't really care about the complexity, how we implement it, okay, right? We first wanted to find the limit.
Okay.
Right? I'm not saying that this is one thing we can use, but having said that, actually this random codebook generation idea was used in practice in network coding. So there you actually specify the code, so you randomly generate a code and actually put your code as a part of your message, and then decoder can actually look at the code and just use it to decode it, because in the end, if everything is linear, all you need to do is just the inversion at the end. So you can get a nice polytime algorithm. And people actually, where is Sid? Maybe he left. So Sid Jaggi, he's around, and his earlier work is how to use actually this random coding in the right context.
Excuse me.
Yes.
Digression, but what you're saying is not very clear. I understand that if we choose a random code, we can encode very fast, just linear operations works in quadratic time. But don't we need an exponential search to decode?
If you use the linear code, so suppose that this hashing is linear, so you just take the coefficient randomly and then do the linear combination, then you are gonna get the matrix. So you need say n cube and max to invert it, assuming that there is an inverse.
We combine several linear.
Yeah, right. But in the end, from the message to the end, it's a linear operation, right? So.
And then we are solving the linear system.
Yes. Yeah. Any other question? But here, actually, I'm not using even anything linear. Here, I'm just doing the nonlinear hashing, and I didn't care about the complexity. But we can at least characterize what we can achieve. And of course, it remains to the coding theories to come up with low complexity codes. Anyway, so this is kind of two snapshots from what you know about the lower bound on the capacity or upper bound on the broadcast rate. What I wanted to discuss mainly for today's talk is actually this upper bound on the capacity or lower bound on beta, broadcast rate. And the first bound I'm going to talk about is maximum acyclic induced subgraph bound, or in short, MACE bound. So here you have the graph, and you observe that 2 and 3, if you look at this subgraph, then it doesn't have any cycle. So we look at the largest subgraph that has no cycle, right? And that number, the size of the subgraph, is actually a lower bound on the broadcast rate. And this result is due to Balyosab, Birk, Jairam, and Cole, right? And I'm going to prove the bound pretty soon. Okay, actually, I'm going to give you 2 proofs, right? But it is not tied in general. But this is our bottom line. So I'm going to prove this bound using directed cassette. So I'm going to first represent this graph in this network coding format. And for simplicity, I'm going to make all the edge links as infinite except this bottleneck link, which has edge link of 1. Okay? And then I'm going to write down. So here is an example, but this one can be scaled very, very easily. So now I'm going to have 3 layers. Okay, and I designed it so that top to bottom, I have this link going down. Okay, and none of this infinite capacity link is actually going down. Okay, because that'll cause some trouble. So this is a physical network. And now, what is the flow here? Logically, this is a flow. We have source 2 going to destination 2 and source 1 going to destination. So now if you look at the directed cassette, what are the flows that is cut? This one is cut and this one is cut. Okay? So there are some rate must be upper bounded by the directed information induced by outputs here and inputs here. Okay? And this one actually can be shown as that is all the edge capacities from nodes on this side first and second floor to the ground floor, as well as second floor to the first floor. This can be checked very, very easily. Okay? Just like the way you are going from Coset bound, the Elgamow's Coset bound, to max flow mean cut theorem. Okay, so that means that twice symmetry capacity is less than 1. In other words, broadcast rate should be greater than 2. And you can generalize this program very easily. Okay? And as a relaxation of Mace bound, there is actually Miss bound. I don't know whether they really called it Miss, but I named it anyway because I was the first to name it. So in this case, now we look at this graph and we look at the maximum independent set. And then we note that 2 and 3 is maximum independent set. And that is actually a lower bound on beta, which you should already know from the previous bound. Okay? But anyway, I mean, again, this result should be attributed to these people, the same set of authors. And this maximum independent set size is called alpha in graph theory, typically. So this alpha is less than beta. I mean, just nice mnemonic. And in this case, actually, what's going on is this is Coset bound. So Coset bound is exactly same as Miss bound. And Mace bound is same as the directed Coset bound. Here is a more general bound, okay, which you call polymatroidal bound or maybe polymatroid bound. I don't know how to phrase it properly, but the idea goes back to Young and Zhang in 1999. And then it was, I mean, in the context of network coding, there is a nice survey paper by Doherty, Freidling, and Ziegler, okay, and in the context of network coding, Blesek and others also wrote a paper, and it goes like this. So we define B as everything that is not in A. So what you don't have is called B. And then the symmetry capacity is upper bounded by minimum of the function difference, the set function difference, f, j and bj, and just bj. And this f should satisfy these properties. This polymatroidal structure. So 0 is 0, empty set is 0, the whole set is 1, and then it is monotonic, and it is submodular. So you look at any f, okay, satisfying this, and then it can bound the symmetry capacity, depending on the structure of the problem you have. Okay? So how do you do it? We look at 2 to the n dimensional, 2 to the n minus 1 dimensional polymatroid here, and then we project it in certain direction, okay, which is given by the side information pattern we have. Okay? So that is a bound. So overall, the bound itself has a nice polymatroidal structure, okay, and later John Walsh will talk about some of the computational aspects related to this type of bounds. Unfortunately, this is not tight in general. Okay, again, done by Rees Group as well as Syed Jafar and his student in 2013. So we actually know that non-Shannon type inequality is actually needed to improve this bound. Here is the proof sketch of polymatroidal bound. Okay, I mean, we just generate x's at random. Okay, and output is its function mapping. Okay, and then we define the f of s as the ratio between the h of y and h of y given x of s complement. So for every set s, we define it this way, right? Then the rate condition goes like this. T is the number of bits. And since we assume that the messages are uniformly distributed, so it is exactly same as h of xj. And since y is function of all the messages, and x's are independent of each other, right? We assume that the messages are independent. And therefore, it is equal to this mutual information. We can write that. Write it this way. Okay. And then from our definition, it is given by this. And finally, we are spending only r bits. H of y should be upper bounded by r. So this is actually the only place we have the upper bound. And therefore, the rate T over r should be upper bounded by these differences between f. So that is a rate constraint. The boundary conditions, okay, if you have everything, then y is function of x, so it is 0. When you have nothing, then it is h of y. Okay, so there is nothing. Monotonicity, I mean, it's clear since conditioning reduces entropy. And finally, the submodularity. This submodularity is not directly The entropy submodularity, but it's essentially the same idea. Okay? So that is how we come up with this bound. Here is one way we can prove the maze bound from polymatroidal bound. Okay, so from polymatroidal structure, we actually have this. If j is less than k, okay, then fjk minus fk should be upper bounded by fjj and fj for any j and say any element j and any set j included in k. So now let's just take an example graph. This one, and if you look at set 1, 2, 3, then it is acyclic. So let's just look at that one. Then the symmetry grade for this one is less than 1, 2, 3 minus 2, 3, right? I mean, 1 has 2 and 3 as non-side information, right? So the rate for receiver 1 should be upper bounded by this. And the second one should be upper bounded by, say, from 2, 1 is there. So 3 and 4 are B. So we have this constraint. And if you look at this one, 3 has 1 and 2, but not 4. So we have this constraint. So these three things follow from polymatroidal bound. And finally, using the lemma, we remove everything that is not in 1, 2, 3. So we keep this one. 4 is removed. And this is still a valid bound because of this. And 4, again, we can remove it, so we get this. And now we observe that they telescope, right? So we can see that 3 times C sum should be less than F of 1, 2, 3, which is 1. So that is how you get it. And this can be generalized because if you have any acyclic S, then there is some permutation pi so that the side information, the non-side information is there only if we are going in an increasing order, just like this. So here, 1 has 2 and 3 in non-side information. 2 has only 3 in non-side information, and 3 has nothing. So there can be some degradiness in side information pattern. So this way, we can go from polymatroidal bound to the maze bound. Okay, so here is a hierarchy of capacity upper bounds. So for index coding, I believe we have a clean picture, and there can be some subdivisions, at some point. So we can have miss bound, and then we have a maze bound, then we have a polymatroid bound, and then we have entropic bound. The general network, now we know two things, right? I mean, we have coset bound, which is exactly same as this. We have directed coset, which is exactly same as this. This bound, we don't know yet. Okay. But I mean, with enough hint, I believe that somebody can figure it out pretty soon. Okay. And then, of course, there is the fundamental bound. So let me summarize. Probably through this talk, I could convince you that index coding is the most important problem in network information theory. Through applications, through motivations, connections to other problems, and through its just pure form. I mean, it's a pure problem. Let me give you a few more open questions other than the question marks we had before. The first is Chan and Grant in 2008 show that there is a nice and precise relationship between all entropic inequalities versus network coding problems. So for each network coding problem, actually there is a corresponding inequality that is needed to characterize its capacity region. Okay, so can you actually run the same program for index coding? And I believe the answer should be yes, because the problem is much simpler. We are not really cluttered by the network topology or anything. I mean, here, I believe that we can write things in a very, very simple manner, but haven't figured out how. And second thing is, if you look at the network coding literature, okay, I'm not blaming anybody, but the literature is very, very messy. Okay, so there are many, many bounds that was proposed as an upper bound on network coding capacity, and it is unclear how their hierarchy, is really there. I mean, there are some results say, I'm doing better than the other. Okay. But they don't show actually I'm strictly better than the other, and so on. Okay, and because of that, and some of them actually don't compare. So there are many bounds, and let me just mention some of them. There is a linear programming bound, okay, which is just looking at the polymatroidal structure of entropies. There is an edge cut bound, there is an information dominance bound by Harvey, Kleinberg, and Lehman. Functional dependence bound by Thakur, Chen, and Grant, I believe. Okay, and generalized network sharing bound by Kamath and others. So LP bound is exactly same as our polymetrical bound. So there is a one-to-one correspondence. GNS bound is actually exactly same as Mace bound. So these two things are clear. The question is where these guys belong to. Okay. Are they really collapsing to each other, or is there something more? So this is probably something network coding people should try to sort out. Okay.
I think functional dependence bound is a special case of LP.
Right, but how is it actually? Is there some LP bound that is strictly better than this? Because this one captures actually every function relationship. So my guess is actually this should be same as LP in the end, unless you are doing some relaxation in LP. So. Yes, yeah.
I think LP is much more than functional. I think it has a mutual dependence, but not just functional.
Okay, right. So and they claim that their bound is better than information dominance. Okay, but I don't know whether that is a strict inclusion. And edge cut and information dominance, a lot of people believe that actually they are the same, but nobody verified it. Okay, and GNS bound is weaker than these bounds, right? But we don't know whether it is strict or not. Okay, so that is that much I know. Okay, and how about approximation? I mean, some of these bounds can be actually good to approximate the capacity, but here is what you know. If you are given a general network, say let's first look at some special case. Every edge is bidirectional, say, going this way and the other way, so bidirectional, or there is no edge that is bidirectional, and we call that as unidirectional. So for that case, we can actually approximate beta multiplicatively in the factor of n over log n. Okay? And if you think about it, beta is some number between 1 and n. So approximated using n over log n is not a lot of stuff. Okay? And for general network, then it is actually even worse. It is n of log n over log n. Okay? So right now, there is no bound whatsoever that is actually polynomially good. So say n to the 0.9999 approximation doesn't exist. So I think this is probably the most modest open question for anybody who's working on index coding. Just come up with a multiplicative gap that is m to the 0.99. And for some classes of graphs, we made some progress. We could get, say, n to the 2/3 and so on. But the general graph, the answer is quite elusive. So let me stop here. Thank you very much.